This video, we're going to write down some basic definitions. The first definition is going to be what we call the natural numbers. They are also called the counting numbers. And they have a symbol. Since I can't write in bold, so basically it's bold N. But since one can't write in bold, in text they can. What we do is we put a second line. That stands for the natural numbers. The natural numbers, or the counting numbers, well, just ask yourself how you count. 1, 2, 3, and so on. Since it's a set, I put the values that the counting numbers can be in set brackets. It's the set of numbers 1, 2, 3, and so on. That is 4 is in here, and 5 is in here, and 99 is in there, and 2011 is in there. 1 2/3 is not in there. The next set that we're going to talk about will be the whole numbers. The whole numbers, they're represented by boldface W. We put another line there to signify that it's boldfaced. And the whole numbers, they contain each and every natural number. 1, 2, 3, 4, forever and ever. And the digit 0, the number 0. The next set of numbers that we're going to talk about will be the integers. They are boldface Z. You put the double line there. The integers, well, they contain all the whole numbers. 0 and 1 and 2 and 3 forever and ever. And they also contain -1 and -2 and -3 forever and ever in the other direction. Now that we have the integers defined, we can talk about rational numbers. The rational numbers, they are denoted by boldface Q. We just put another line there. And they are the set of all fractions where A and B are integers. That is, the numerator and denominator comes from that set Z. But the denominator can't be 0. You can't divide by 0. Even if you tried, you can't. For example, if one asks you, what's 10 divided by 2? You would say 5, because 2 times 5 equals 10. Well, if I ask you what 8 divided by 0 equaled, whatever you tell me, if you tell me 8, well, 0 times 8 is not 8. If you tell me 18, 0 times 18 is not 8. If you tell me -8, 0 times -8 is 0. It's not -8. No matter which number you put in this box, no matter which number you put in there, 0 times that number will equal to 0, which is not 8. There's no number that you can put in there. back to this one, an alternate way of seeing it. 2 into 10. Well, maybe it's 1. Well, 2 times 1 is 2. That's less than or equal to 10. Let's try 2. 2 times 2 is 4. That's larger than 2, but it's still less than 10. Or equal to 10. Let's try 3. 2 times 3, 6, is less than 10. Maybe we can do 4. 2 times 4 is 8. That's not bigger than 10. Let's try 5. 2 times 5 is 10. Oh, that's the one. Well, if you try to do 0 into 8, well, maybe I'll put 11 here. Well, 0 times 11 is 0. Let me try another number, 114. 0 times 114 is 8 or less. Let me try 1140. 0 times 1140 didn't exceed 8. Let me try 1,140,762. Well, 0 times that number didn't exceed 8. In other words, I can make this as big as I want. 0 times this extremely large number didn't pass 8 yet. You can't divide by 0. You'll never get an answer. You may say, well, you didn't have remainders. Fine. 13. 2 times 5 is 10. That's not bigger than 13. 2 times 6 is 12. That's not bigger than 13. But 2 times 7 is 14, which is bigger than 13. So I'll take away 2 6s, or 12. Well, that gives me 1. So goes in 6 1/2 times. You're not getting an answer like that with 0. You can't divide by 0. That is, that denominator cannot be the number 0. Now, let us talk a little bit about these sets. Counting numbers. In this set, you have the number 7, even though you don't see it. These 3 dots tell you to see it. 1, 2, 3, 4, 5, 6, 7. There shouldn't be 4 dots. The 3 dots tell you to see the 7. 212 is in there. 999 is in there. The number 10,000 is here. It's well past 3, but it's there. Just like the whole numbers. 17 is here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then 18 and 19 and 20 and eventually 999 and 10,000. There's lots and lots of numbers after the 3 dots. The integers, well, they have all the whole numbers. They have 0 and 1 and 2 and 3 and 4 and 5 and 6 and eventually 17 and eventually 29. But they also have the negative integers, the negative whole numbers. -1, -2, -3, -4, -5, -6, -7, -8, and so on. The rational numbers, they're fractions. Take one of the integers and divide it by another integer that isn't 0, and that number's in Q. You take -5 and you divide it by 17. That number is a rational number. You just can't take 3 and 0 because you can't divide by 0. And even if you could, it says a rational number cannot have the denominator being 0. So let's make it 10. Those are rational numbers. Now, let's play some true-false games. So let's have this set in front of us. The natural numbers are the counting numbers, the whole numbers. There's 0 and 1 and 2 and 3 forever. They're integers. They have 0 and 1 and 2 and 3. They have all their whole numbers. And the negative counting numbers, -1, -2, -3, and so on to the left. And the rational numbers, they're in the form of A over B, where A and B are integers, and B is not the number 0. So we have 4 sets. Notice that I have 2 on the top. 1, 2, 3, and 4. True or false? Every integer is a whole number. Call that number 1. Number 2, and every only has one E. All whole numbers are rational, or rational numbers. Some integers are whole numbers. Oops, 4. Some whole numbers are natural numbers. And number 5 is no integer is a rational number. Guess I should put question marks here. And let us consider the first one. It says every integer. That means each and every integer is a whole number. Well, maybe it's true, maybe it isn't. That's a whole number, I know. I see it right there. 3 is a whole number. It's right there. Oh, yeah, 0 is a whole number. Yeah, looks like every integer is a whole number. But you have to investigate further. -1 is an integer, but I don't see it here. So the answer is false. It says all whole numbers are rational numbers. Well, remember, rational number is the division of 2 integers. 0 and 1 and 2 and 3, etc. Those are whole numbers. But you know what? If I divide by 1, if I divide them all by 1, you know what? That's a rational number. The top number is an integer. I know it is because there's 0 right there. And the denominator is an integer and it's not 0. 1 over 1. The top and the bottom, like I just said, they're integers and the bottom's not 0. 2 over 1. 2's an integer and 1's an integer. And the bottom number is not 1. 3 over 1. 212. That's a whole number divided by 1. So it says, all whole numbers are integers. Yes. No, sorry. All whole numbers are rational numbers. That's true. Because all I have to do is take every rational number and divide it by 1. And let me try that again. All I have to do is take every whole number and divide it by 1. And I get a rational number. Here are some rational numbers. There are some rational numbers. And then when I divide them by 1, they still equal. This number is still 0. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 212 divided by 1 is 212. I was able to write each and every one of these whole numbers that I listed as a rational number. All I have to do is divide those rational numbers. All I have to do is take these whole numbers. I take the whole numbers and I divide them by 1, and they're still equal to themselves, the same starting numbers, and they are now rational. So yes, this is true. Now it says that some whole numbers are natural. Well, it doesn't say every whole number are rational. It doesn't say no whole numbers are natural numbers. It says some. This number right here is a natural number. There's my sum. This is true. I mean, you can say 1 and 2 are whole numbers that are natural numbers. That can be your sum. Or you can just say 2's a whole number and it's also a natural number. The next one says no integer is a rational number. Now that's not true, because every integer, 0, 1, 2, 3, 4, 5, etc., and -1, and -2, and -3, and so on, they all equal to 0 equals 0 over 1, 1 equals 1 over 1, 2 equals 2 over 1, 3 equals 3 over 1, 4 equals 4 over 1. I can say that 5 is 10 over 2. I can say that 6 is 18 divided by 3. Or I can say it's 5 over 1 and 6 over 1. -1 is -1 over 1. -2 can be thought of as -2 over 1. -3, if we like, you can think of it as -6 over 2, which is also -3, or -3 over 1. Either way, each and every integer, and you have to make sure that this statement is true even after the dots. Every integer, that is, these integers, which equal the number or numbers below them, has been written as a fraction of 2 integers. -6 is an integer, 2's an integer, and it's not 0. I wrote -3 as a rational number. -2's an integer, 1 is an integer, and it's not 0, so this fraction is rational. This is an integer, that's an integer, the bottom's not 0. That's a rational number. Well, if this number is rational, and it equals to this number, that number is rational. Every integer is a rational number. This says that no integer is a rational number. That couldn't be any more false. How about a couple more? All rational numbers are integers. And how about some rational numbers are integers? Well, this says each and every rational number is an integer. Well, no. 3 over 2 is a rational number because the top is an integer, the bottom's an integer, and the bottom's not 0. 3 over 2 is a rational number. Good luck trying to find it in the set Z. Of course, another rational number would be 7 over 1, or let's try a different number. 15 over 3. Well, that's 5. This is a rational number. The top number is an integer. The bottom number is an integer, and it's not 0. But it's 5. And if you go out far enough, you'll see 5's an integer. But not all rational numbers are integers. This says that well, let's see where we're up to. This says all rational numbers are integers. That's false, because 3 over 2 is a rational number, but 3 over 2 is not an integer. What about some rational numbers are integers? Well, just said. 15 over 3. The top is an integer. The bottom's an integer. The bottom is not 0. 15 over 3 is a rational number. But you know what? It equals 5. And this is an integer. Okay. I want to end this video by talking about one more set of numbers. Remember that we said the rational numbers is the set of all fractions where A and B are integers and B is not 0. That is how we defined the rational numbers. The irrational numbers are numbers that are not rational. The prefix IR means not. It's not rational. For example, the square root of 2 cannot be written as the division of two integers. Some point past basic arithmetic, you should see a proof showing that. The square root of 3 is irrational. The square root of 4 is equal to 2, which I can write as 2 over 1 or 12 over 6. That is not irrational. But the square root of 5 is, the square root of 6, the square root of 7. All the integers you do not know the square root of. I know the square root of 9, it's 3, which is 3 over 1. So that one's gone. I don't know the square root of 10. Comma. I do not know the square root of 11. I do not know the square root of 12. I don't know the square root of 13. I don't know the square root of 14. I don't know the square root of 15. But I do know the square root of 16 is 4, which I can think of as 4 over 1 or 12 over 3 or negative 8 over negative 2. So that gets knocked out. And you have the square root of 17 all the way up to the square root of 24. The square root of 25 is out. The square root of 26. So all of these numbers are irrational. You cannot write any of these numbers as the division of two integers. You cannot write these numbers as the division of two integers. Those are irrational. Decimal numbers that repeat, like pi, is 3.1415925, and it goes on and on, but it doesn't repeat. It does not repeat. For example, if you have 0.11 and then a 0, and then 2 ones and a 0, and then 3 ones and a 0, and then 4 ones and a 0, and then 5 ones and a 0, etc. That is irrational. You may see the pattern, but nothing's repeating. Repeating would be 2, 3, 2, 3, 2, 3. And you can have a 7 in front. As long as, etc., forever and ever, your 2, 3 keeps repeating. It doesn't have to repeat at the beginning. Like if you have 723.15243434343. These two numbers, they can be written as the division of two integers. They can be. If you say no, they can't, they're less than, it has the fractional part. Well, 3 over 2 has the fractional part. It's 5. But I still wrote it as the division of two integers. So numbers that go on forever, but they don't repeat, they are irrational. Numbers that you do not know the square root of, integers that you do not know the square root of, they are irrational. There's this number e. Just like pi, there's a number e. It is 2.718, and it goes on forever. And the forever part doesn't repeat. Okay, it didn't repeat like in 723.124628171717 and the 17 repeats. This is a repeating decimal. You can write this as the division of two fractions. These 3 dots are telling you that the 17 keeps repeating. Here, nothing repeats. Not forever. For example, E might be 2.718324, and then 718, maybe 324 again. But that won't repeat. Next will be 38912. Of course, if you have an infinite number, a string of an infinite number of digits, you might see your pattern repeat here and there. but it won't be repeating like this did. 171717 forever. Okay, repeating one time is not enough. It has to repeat forever and ever. This number would be irrational because it doesn't repeat. So let's get rid of this one. And pi is irrational. This number is irrational. Even though you know the pattern, it's the pattern you may know the pattern, but it's not repeating. This number doesn't repeat. It is irrational. This number down here does not repeat. Those are irrational. The square root of 2, it is irrational, meaning that it goes on forever as a decimal number that doesn't repeat. So now you know how to find two types of irrational numbers. Numbers that you do not know integers, or whole numbers that you don't know the square root of, and decimal numbers that go on forever but they don't repeat. There's a decimal there. They don't repeat. It's a decimal number that goes on forever and ever without repeating. And it turns out that the square root of 11 and the square root of 26, the numbers you don't know the square root of, they cannot be written as a finite decimal number. It will be a decimal number that goes on forever and ever and does not repeat. What's an irrational number? It's a number that has, it's a decimal number. That means when I say a decimal number, it can have numbers before the decimal and it has numbers after the decimal. And if what comes after the decimal goes on forever, that is, there's no ending, it's a non-ending decimal number, and it doesn't repeat. 1, 2, 3, 4, 5, 5, 2, 1, 8, 3, 7, 4. This number is irrational. That's going to complete this video.